All right, so to start up, we're going to go over 7.10 and negative exponents. But we're going to start with a warm-up kind of to review the things we've seen before. They want us to evaluate each expression for the given values of the variable. So let's plug in the -1 for the x. So -1 to the third power times 10 to the second. So -1, so it's going to be -1 times -1 times -1. That's going to be -1. And then 10 to the second power is 100. So it's going to be -100 as our answer for the first one. Now for the second, we're going to have 3 times 4 to the second power over -7 to the second power. That's going to be 3 times 16 over 49. So this is going to be 48 over 49. Now I'm just going to leave it as 48 over 49. Just to leave it as a fraction. Now for 3 and 4, they want us to write each number as a power of the given base. So 64 base 4. That's going to be 4 to the third power. And then, because 4 to the third power equals 64. And then for the last one, it's going to be -3 to the third power as well, because -3 times -3 times -3 is going to give us -27. So our goals today are going to be able to evaluate expressions containing 0 and integer expressions, simplify expressions containing zeros and integer exponents. That's our objectives. Those are our goals for the end of the lesson. Now let's recall exponents. We've seen them before. We just didn't go as in depth as we are going to go today. Our base is going to be that number in the bottom, the big number, and the exponent is going to be the small number at the top. So if you have an example of 4 to the second power, our 4 is our base. Our 2 is our exponent. That's always going to be the case. You may have letters, you may have numbers. In this case, in the example, we have the x, which is a letter, and then in our example that we just made up, it is a number, but it's still called the same thing. So you have seen positive exponents, so recall that 3 to the second power is 3, and you use the factor 2 times. So 3 to the second power is 3 times 3, so we get 9. But what does it mean when you get an exponent of a negative or a 0? You can actually use a table to look for a pattern to figure it out. So if you notice, as we go up, we multiply by 5. So usually you've gone from a 1 exponent to the second, and we always end up multiplying. So if we're going backwards, we actually end up dividing. So if we're going from bigger to smaller, we end up dividing by that same base value. So if we divide 5 divided by 5, we're going to get 1. If we divide by 5, it's going to be 1 over 5. And if we divide by 5 again, it's going to be 1 over 25. Now, this is a rule. It's never going to change if you have an exponent of 0. So let me see where I can write it so it fits. A 0 exponent. Your answer will always be 1. Now, obviously you can figure it out by 5 to the first power is itself. So you end up with 5 to the 0 power dividing by 5 to get the 1. But this is always a rule. So if you have a number 7,563 to the 0 power, this is still going to be just 1. It's never going to be different. That's always going to be the case. So we have integer exponents. So 0 exponent, any non-zero number raised to the 0 power is 1, so like what we just went over. And then you have negative exponents. A non-zero number raised to a negative exponent is equal to 1 divided by the number raised to the opposite positive exponent. So this is just a lot of words. I'd like to look at the examples first. You notice if we have, I'm just going to rewrite it, 3 to the negative second power. This negative doesn't mean that the answer is going to be negative. all that means is that it's not in the happy place. Remember, every number is over 1. So that negative means that it wants the 3 to go to the bottom. That's all that means. And after that, we just treat it as if it were everything we've seen before. So equals to 1 over 9. And that will be your answer. Now, if by any chance you have, let's say, 2 to the negative 3, again, doesn't mean that negative at the bottom of the fraction is it's going to be negative. It just means it's not in a happy place. So we're just going to flip it 2 to the 3rd power. So we're going to get 2 times 2 and times 2. So it's going to be 8 as your answer. So all that means is it's going to flip it over. Doesn't matter if it starts at the top. Doesn't matter if it starts at the bottom. And that is true also for variables, not just numbers. So the way you read a negative exponent is, for example, we have 2 to the negative 4, and it is read as 2 to the negative 4th power. Now, when I speak, sometimes I forget to say the word power, but it's still, I should say it. So 2 to the negative 4th power. That's how you read it. If you had something else, like 3 to the negative 2nd power, you need to add the word power. If I forget to say the word power, I'm sorry, just in advance. I would usually read it as 2 to the negative 2nd. But key word is you should say power. It tells you what it is. So let's solve this one together. So we're going to have 1 over 2 to the 4th because we have this negative. Again, it doesn't mean it's unhappy. It doesn't mean it's negative. It just means it's in the wrong place. So we're going to do 1 over. I'm going to write it 2 times 2 times 2 times 2. So this is 4. This is 4. So we get 1 over 16. That's our answer. So let's run through these examples. So negative 1 over 4 over 3. That's going to be 1 over 4 times 4 times 4. That's going to be 1 over 16 times 4. And 16 times 4 is 64. So we get 1 over 64 as our answer for the first one. For the second one, it's just going to be 1. Remember, anything to the power of 0 is just 1. And for the last one, we're going to have 1 over negative 5 to the 4th. Because of this negative, it's going to be 1 over negative 5 times negative 5 times negative 5 times negative 5. So it's going to be 25 times 25. And that's going to be 1 over 625. So now they want to evaluate the expressions for the given value for the variable. So when we plug it in, we're going to get 4 to the negative 2nd power. So it's going to become 1 over 4 to the 2nd power. So it's going to become 1 over 16. So let's plug in the numbers to figure out how to simplify this as much as we can. So the negative 2 stays the same because there's nothing to do with that. Our A is 5 to the 0 power. And our B is negative 3 to the negative 4th power. So the first thing when it comes to this type of problems that I like to do is to figure out the exponents. Well, you guys know PEMDAS, parentheses, exponents, multiplying, dividing, adding, and subtracting. So there's nothing we can do for multiplying until we get rid of the exponents. Our term 5 to the 0 power is 1. So I'm just going to write negative 2 times 1. And then our term with negative 3 to the negative 4th power is 1 over negative 3 to the 4th power. So I'm going to rewrite it a little more simple by multiplying negative 2 times 1. So I'm just going to get negative 2 times 1 over negative 3 over 4. Negative 3 to the 4th power. So that's going to be negative 2 over negative 3 to the 4th power. So that's going to be negative 2 over negative 3 times negative 3 times negative 3 times negative 3. This is 9. This is 9. So we're left with negative 2 over 81 as our final answer. Okay, so let's plug in. It's going to be 4 to the negative 3rd power. So that's going to be 1 over 4 to the 3rd power. So it's going to be 1 over 4 times 4 times 4. So 16 times 4. 16 times 4. I don't know why I wrote times 6. Times 4, sorry. That's going to be 1 over 64. So let's plug these in. So they're asking us to evaluate the expression for the given values of the variable. So we're going to have 8 times negative 2 to the negative second power, 6 to the 0 power. Now again, like I did before, I like to get rid of the stuff that I can as soon as I can. 6 to the power of 0 is just going to be 1. And the negative to the negative second power is going to be 1 over negative 2. So I'm going to write 8 times 1 over negative 2 to the second power times 1. I'm going to simplify this by multiplying the numerators together in the denominator. So I'm going to get 8 over negative 2 to the second power. That's going to become 8 over 4. And that's going to simplify to 2 as our answer. So what if you have an expression with a negative exponent in the denominator, such as 1 over x to the negative 8? This is just what we went over. If it's at the bottom, you move it to the top. Like we had 1 over 2 to the negative second. That just means that it's going to be 2 to the second power, so that's just going to be 4. So again, the negative in the denominator doesn't mean it's negative. It does the same function. If it's on the bottom, you move it up. If it's on the top, you move it to the bottom. So an expression that contains negative or 0 exponents is not considered to be simplified. An expression should be written with only positive exponents. So as you guys are simplifying, you do want to make sure you flip over the negative exponents, as you always want them to be positive. That is going to be very important as to simplifying the expression. If you have a negative exponent as the answer, that answer is technically wrong. So let's simplify this one together. Let's start with the negative exponent and the zeros. So looking at this, we have an a to the 0 power, so it's going to become 1. So I'm not gonna worry a lot about it. Let's look at the other exponents. We have a negative 2 and a negative 3 right here. So you want to make sure we flip those. So we're going to get c to the 3rd power, because we're flipping this one up, over b to the 2nd power, because we're flipping that one down, d to the 6th. That's all you have to do to get that answer. Now, I know we technically have that times 1 from that a to the 0 power, but since it's times 1, everything that's multiplied by 1 is just itself. I'm not going to write it, or I erased it here, to get the final answer of c to the 3rd power over b to the 2nd power times d to the 6th power. So just like we move negative exponents, the ones that are already opposite, you just leave in that place. You don't have to move them around. So for a, we got to look at the exponents. This was the only one that's negative. So all I'm going to do is flip it over into 7 over w to the 4th power. Now, for the second one, we're going to realize that this k, we have a negative exponent. So what we're going to do is move it to the top. So 5 times k to the 2nd power. The 5 should be negative. I just forgot to write it. Now, for A, B, and C, the one is again to just simplify. So in order to do that, we're going to look at the exponents. This r to the 0 power is just 1. So anything times 1 is just itself. So I'm just going to cross it out for now. I'm just going to write 1 up here, but it's not going to do anything for us. Now, 2 times m to the negative 3rd power. This negative power, we want to make sure we flip it. So since we have this negative, we're going to flip it over to 2 times 1 over m to the 3rd. It's going to combine into 2 over m to the 3rd. If you're able to just go from the first to the last step, that is fine. A lot of these don't require a ton of work. Now, for b, we have this negative power. So again, we're going to flip it over. So 1 over 7 r to the 3rd power. Again, we just flipped it over. Then we have the negative 6. So we're going to go flip it up for the c. So it's going to be g4 times h to the 6th power. So these are your 3 answers for 8, b, and c. So let's recall the properties of exponents. We have the properties of exponents are, you can use properties of exponents to multiply and divide powers with the same base. consider the following three cases. For example, 4 to the 5th power times 4 to the 2nd power. What you end up doing is adding the exponents. When you have the same base, we add the exponents. Like they said, the bases of the powers are the same. So to multiply powers with the same base, we add the exponent. So 4 to the 5th power times 4 to the 2nd power equals 4 to the 7th power. That looks like a division, but it's a plus sign. For example, when you have 4 to the 5th power divided by 4 to the 2nd power, in this case, we subtract the powers. So we would do 5 minus 2. Let's read what it's stating. The bases of the power of 4 are the same, so divide powers with the same base. Subtract the exponent. So 4 to the 5th power divided by 4 to the 2nd power is going to equal 4 to the 5th power minus to the 2nd power. So you end up with 4 to the 3rd power. Now, for the third one, it says the bases of the powers are not the same. The exponential properties of multiplication and division illustrated above does not apply. So the key part here, guys, is it has to have the same base. So if we have x squared times x cubed, we're going to get x to the 5th because we add them. If we have x cubed divided by x squared, we're going to subtract, so we're going to get x to the 1st power, or just x. We'll get to some other properties as we do examples, but these are the two that this slide covers. So these are the other rules I was mentioning that we would do later. This is later. So properties of the exponents, we have the power of a power property. So this property states that to find the power of a power, we multiply the exponent. So if we have x to the n power, then we're going to get x to the n times n power. So for example, if we have 8 to the 2nd power, all of that raised to the 3rd, we're going to have 8 to the 2 times 3 for the power. So we're going to get 8 is equal, or 8 to the 6th power. Now, I am going to do all of a summary of everything we've done so far, just to have it. Okay, so far we have multiplying powers with the same base. So we're going to end up adding, so x to the 5th. We have division, x to the 3rd divided by x to the 2nd. We end up subtracting, so it's x to the 1 or just x. And then for the last one, we're going to get x to the 3rd power. All of that raised to the 2nd power, so it's going to be x to the 6th because we end up multiplying the 3 and the 2. Those are the rules for these. Now, again, the key part is the same, has to have the same base. If it doesn't have the same base, guys, you cannot apply these rules. So here are the laws of explanations that follow. X to the 1st power is just itself. Anything to the 0 power is 1. When you have a negative exponent, it flips the fraction over. When you have the same base and you're multiplying them, you're going to add the exponents. We're right here. Then if you're dividing right here, we end up subtracting the exponents. If you have them to the power, raised to the same power, we're going to end up multiplying them. If you guys have two numbers and one exponent, we're going to end up distributing those like this into x to the nth power and y to the nth power. The same thing happens if it's a fraction. We're going to end up distributing the power to both terms into the fraction form. And if you have a x to the negative n power, it's going to be 1 over whatever the power is at the bottom. And you have the law about the fraction exponents. That is, if you have, for example, x to the 3/2, this is going to be the same thing as if you do the square root of x to the 3rd power. This didn't explain it a lot, but what does this mean? If you have a power of a fraction, let's say a half, it's always going to be the square root of something. Or if you have x to the 1/3, it's going to be the cube root of x. If you have x to the 1/4, you're going to be the 4th root of x, and it's always a case. That is always the denominator for the fraction of the power. Now the numerator, if we were to change it, let's say this is now 2. This is going to become the entire thing to raise to the 2nd power. Let's say this is to the 5th power. This is now all of it raised to the 5th. This is just different ways of writing it. there's not a lot of examples on this, but for example, I'll make one up. If we have 27 to the 2/3 power, right? It's going to look like this. 27 and then to the square. Now, in this case, it does not matter if you square it first or if you take the cube root. Now, ideally for 27, it's going to be a lot easier to take the cube root first because that's just going to be 3, because 3 times 3 is 9 and 3 times 9 is 27. So we're going to get 3 to the 2nd power. So we end up with 9 at the very end as our answer. So you can do it either way. Sometimes it's easier to subtract first. Sometimes it's easier to multiply first. Sometimes it's easier to take the cube root first. Sometimes it's easier to square it. In this case, I took the cube root just as an example. You guys have practice problems with these. I took these off on the other problems. But this is it for the nodes.